Good morning everyone. I am Tanushree from Civil Engineering branch, and today I am going to teach you your Theory 1 paper which name is Structural Mechanics. And we will start today your chapter number 6 which name is Slope and Deflection. Basically, this chapter is related to your chapter 5, that is shear force and bending moment. Here the two major terms, that is deflection and slope, you have to analyze from the beam section that may be a cantilever or simply supported with the loading system UDL or point loads. And here for each kind of loading system on the beam, you have to determine or derive the equation of deflection and also slope. So first of all, you need to know what do you mean by deflection and slope of the beam section. So let's get started. So first of all, deflection of a beam. So deflection means whenever a beam subjected to a loading system, then due to this loading system, this beam is deformed and deflect to a curvature-like section. So you can see this dotted portion of this figure is defined as the deformation for the loading system in a beam. So due to this loading system, whatever may be the deviated distance compared to the original place of the beam, that portion is known as the deflection. That means you can see here where the point load is subjected to, the deflection value is this much. Okay, this distance will be the deflection value, and the deflection value will be more at that point where the loading value will be more. Okay, so due to the point load is here, so that the deflection value here is more as compared to this and this length of the beam. So we can say the deflection at any point on the axis of the beam is the distance between its position before and after loading. So you can see before loading the position of the beam is horizontally here, but after the loading system the deflection value of the beam is this much. Okay. Then comes to the slope of a beam. So what do you mean by slope? So you can see in a deviated beam section, that means this dotted line, if we draw a tangent line, then the angle between the deviated beam up to the tangent line is known as your slope of the beam. Basically, it is denoted as theta. So as per the definition of the slope of the beam, slope at any section in a deflected beam is defined as the angle in radian which the tangent at section makes with the original axis of the beam. So that means this angle and this angle will be the value of slope for the point load condition in a beam. And the deflection of the beam is also denoted as y. So now comes to the methods for finding the slope and deflection of the beam. So there are so many kinds of methods by which we can analyze the slope and deflection value in a beam with various kinds of loading system. So there are 5 kinds of methods which we can use to find out the slope and deflection. So first one is your double integration method, second one is your macroless method, third one is your area movement method, fourth one is your conjugate beam method, and fifth one is your unit load method. So among these 5 methods, we will discuss about first 2 methods, that is double integration method and Maxwell's method. Okay. So first of all, we will go for the double integration method. So as you see, the name of the method, that is double integration method. In this method, we have to integrate a equation twice time. Okay. The equation is the maximum bending moment value about the x-axis section for the beam. Okay. So basically, it is a technique used in structural analysis to determine the slope and deflection of a beam. Here, we will be able to directly work on the equation of elastic curve. As its name, first of all, find out the curvature equation as given in the figure, then integrate it once. Hence, we can find out the slope value and again integrate the f of equation twice. Hence, we can get our deflection value. So, as you know that the curvature equation is denoted as d square y by dx square is equal to 1 by ei into m. Here m represents the maximum bending moment value. So, according to this method, we have to integrate this equation once. That means dy by dx is equal to e by ei, integrate value of m into dx plus c1. So we know that for the integration value we need a constant. So here integrate once, that means this equation is the equation of the slope. Okay. Then again integration, we can find out the deflection value. Hence y is equal to e by ei double integration of m dx plus integration of constant 1 into x plus ct. So this is your twice integration value. So we can say this value is your deflection equation. Hence, here for the first integration we got the constant c1 and for the second integration we got the value of c2. So now the dy by dx is the value of slope, that means the theta value, and y value is the deflection value. So first of all, we need to derive the equation for a cantilever beam, and here a point load is subjected to at the free end, and what are the derivation and deflection and slope value for this beam we have to analyze. So here we have to determine the slope and deflection for the beam loaded as shown in the figure, that means this figure. Then we have to find out the maximum deflection and maximum slope value. Then here regarding this value we have to find out a numerical, that means we have to analyze the slope and deflection with the value of loading system 6 kN, length of the beam is 3 meter, and Young's modulus is given as 201 GPa, and moment of inertia value is 16 into 10 to the power 2 centimeter to the power 4. So now first of all we need to analyze the slope and deflection value for the beam which is shown in the figure. So first of all, as I told you, we need to know the maximum bending moment with respect to the x-axis section in a beam. So this is your beam section, and here the fixed end support is there, and this one is your free end, and here a point load is provided named as capital P, and here the 1-1 section is there which is at a distance of x from the free end. can say where the loading system is, at that point the deflection value is more. So here is your deflection value, and this dotted line, if we join to this much, then you can say due to the fixed end support, it can't be deflect from its position. So only deflection will be at free end, and at that point we can get our slope value also. So now we have to find out the maximum bending moment up to this much point. Okay. So now for the bending moment value, we know that the bending moment is equal to load into distance. So here loading value is P and distance up to this section is X. So we can say P into X is the bending moment for the section 1-1. So now the sign of the bending moment for this kind of loading system is depend upon the type of moment. So here if P loading is downward in direction, then it will give a hogging moment towards the 1-1 section, that means towards this point. So hence due to the hogging moment, we know that the sign of the bending moment should be negative in nature. So we can say the moment, that means the bending moment for the 1-1 section is equal to minus P into X. Hence, according to the curvature equation, that is EI d square y divided by dx square is equal to bending moment of the section 1-1, which is equal to again minus P into X. So now we got our equation of curvature. Hence, by integrating this value, we can get the slope and deflection value of this beam. So now, if we integrate once to the curvature equation, then we can get EI dy divided by dx, which is equal to minus p x square by 2 plus c1, where c1 is the constant for the first integration. Hence, this equation is your slope equation. Okay, and again integration, we can get the value as EI y equal to minus p x cube divided by 6 plus c1x plus c2. Hence, this is the value of twice integration of the curvature equation. So hence we can say this equation 2 is a deflection equation. Now we have to find out the value of constant, that means the C1 and C2 value, by putting some condition. So now we have to put the condition as at free end when x equal to 0, dy by dx equal to 0. Hence we can put this value in the equation 1. Hence we get the C1 value as 0. As like that, at fixed end when x equal to L and dy by dx is equal to 0, we have to put this condition in equation 1. Hence we get the value of C1 as PL square by 2. Hence we got our first constant value, that is PL square by 2. Now we can put this C1 value in the equation 1. Hence we got EI dy by dx is equal to minus px square by 2 plus PL square by 2. Now this much is the actual value of slope equation for the cantilever beam with point load at the free end. So today this much. We will continue from this much in the next class. Thank you so much.